Imagine standing in the middle of a vast field at dawn. There is no wind, no birdsong, only fog. A thick mist blankets everything, erasing the familiar outlines of the world. You know there is ground beneath your feet, but you cannot see it. You believe there are trees somewhere in the distance, yet you cannot confirm their presence. Within the fog, all things lose their clear shapes. They do not completely disappear, but neither do they truly exist in the way you are accustomed to perceiving. You move forward slowly. Only when your hand touches a cold, damp tree trunk does the world suddenly feel more real. Only when skin meets surface, when the senses are stimulated, does existence seem to be confirmed. Before that moment, everything is merely possibility, a space filled with assumptions, where you cannot be certain what is actually there and what exists only within your own speculation. This is not merely a poetic image or a philosophical game of imagination. It is an almost perfect metaphor for how the world operates at the deepest level of reality, the quantum world. In the everyday world we inhabit, everything appears stable and certain. A table remains there whether you look at it or not. A stone lies on the ground even if no one observes it. Reality, according to common intuition, is a fixed stage on which humans are merely spectators standing at the edge. We believe the world exists independently of our consciousness, that objects possess clear, definite states, regardless of whether anyone is aware of them. But as science pushes deeper, beyond the familiar surface of the macroscopic world, down to the scale of atoms and fundamental particles, that belief begins to fracture. At the quantum level, reality no longer resembles a field in clear daylight. It looks more like the fog-covered field, one where existence is not guaranteed until interaction occurs. Fundamental particles do not behave like tiny marbles sitting neatly at definite positions. They are not there in the ordinary sense. Instead, they exist as clouds of probability, spread out, ambiguous, without fixed form until a measurement is made. Before being observed, a particle can exist in multiple states simultaneously. It does not choose a single path. It does not make a clear decision about its position or momentum. It exists suspended among possibilities, like the foggy field where everything may be present, yet nothing is truly confirmed. And then the moment of observation occurs. Not observation in the everyday sense of seeing with the eyes, but any interaction sufficient to extract information, a measurement, an instrument, a physical interaction. At that moment, quantum reality appears to freeze. From countless possibilities, a single outcome emerges. Like touching the tree in the fog, the world suddenly becomes clearer, but only at the exact point of contact. This leads us to a question that has unsettled scientists and philosophers for more than a century. If there is no observation, does reality truly exist? The question may sound naive, even vaguely philosophical, but in quantum mechanics it is not abstract. It is a technical question, testable by experiment. And time and again, experiments have confirmed it in ways that deeply disturb us. Famous experiments show that the behavior of particles changes depending on whether they are observed. Not merely that we discover what is happening, but that the act of observation itself appears to participate directly in creating the outcome. Reality, at this level, is no longer a pre-recorded film waiting to be replayed. It is more like an improvised performance, where the script is written only when the stage lights turn on. So what is really happening? Does reality require an observer to exist? Or put differently, without any form of measurement, is the quantum world merely a sea of unrealized possibilities? And if that is the case, what role do humans, or more broadly, consciousness, play in the structure of the universe? These questions do not reject science. On the contrary, science itself forces us to ask them. Quantum mechanics is among the most precise theories humanity has ever created. It predicts experimental outcomes with near-perfect accuracy. Yet what is unsettling is this: we know how to use it, but we are not sure we truly understand it. Standing before the quantum world, the familiar sense of a solid reality begins to dissolve. What once seemed fundamental, matter, space, time, grows hazy, like a horizon swallowed by fog. And within that fog, humans are no longer outsiders observing an independent universe, but perhaps inseparable from the very process through which reality forms. The purpose of this journey is not to provide comfort. On the contrary, it is meant to pull us out of the soothing assumption that the world simply is the way it is, that reality is stable, certain, and beyond question. The quantum world forces us to confront a deeply unsettling possibility, that what we call reality may be far more fragile, flexible, and dependent on perception than we ever dared imagine. And this is only the beginning. If our familiar world resembles a smoothly operating machine, where every gear has a fixed place and every motion follows clear causal laws, then the quantum world is more like an unstable dream. There, the rules humans rely on to understand reality begin to dissolve, not gradually, but almost completely. In the macroscopic world, an object can be in only one place at a time. A stone cannot be both on the ground and floating in the air. A car cannot be simultaneously moving and stationary. These ideas are so deeply embedded in our intuition that they seem self-evident. But when we descend to the scale of fundamental particles, that intuition becomes a burden rather than a tool. One of the first concepts to shock scientists was superposition. According to quantum mechanics and theory, unobserved particle does not have to choose a single state. Instead, it exists in multiple states at once. This is not because it moves too fast to track, but because, in a fundamental sense, it has not yet decided where it is or what it is doing. An electron, for example, can be in multiple positions simultaneously. A photon can travel multiple paths at the same time. In this state, the particle is not a small concrete object, but a collection of overlapping possibilities. Only when a measurement is performed, only when an interaction strong enough to extract information occurs, does the superposition collapse, forcing the particle to choose a single outcome. What is unsettling is not that particles behave strangely. What is unsettling is this: before observation, there is no definite reality waiting to be discovered. Observation does not merely reveal truth, it appears to create it. No experiment illustrates this more clearly than the famous double-slit experiment. In it, particles of light or electrons are fired at a barrier with two narrow slits. If no device observes which slit the particle passes through, the pattern formed on the screen behind shows interference, a hallmark of waves. This implies that each particle passed through both slits simultaneously, interfering with itself. But when scientists place detectors to observe which slit the particle goes through, something extraordinary happens. The interference pattern disappears. The particles behave like tiny bullets, passing through one slit only and leaving individual marks, the same system, the same particles. The only difference is whether observation occurs, and the result changes completely. No classical explanation can rescue this phenomenon. It cannot be dismissed as ordinary disturbance because even extremely delicate measurements, barely interacting physically, are enough to destroy the wave pattern. Information itself, the act of knowing the particles' path, seems sufficient to change how reality manifests. From experiments like these, a fierce debate erupted in the 20th century among the greatest minds of modern physics. On one side stood Albert Einstein, who could not accept the idea that reality was so vague and dependent on observation. He believed the world must exist objectively, with definite properties, whether or not humans observe it. To Einstein, quantum mechanics was likely incomplete, missing some undiscovered hidden variables. On the other side was Niels Bohr and supporters of the Copenhagen interpretation. They argued that demanding an objective reality, independent of measurement, was a leftover from classical thinking. According to them, the question, "Where is the particle when it is not observed?" has no physical meaning. Reality in quantum mechanics consists only of what can be measured and described by experimental results. Einstein famously said, "God does not play dice." Bohr replied just as sharply, "Stop telling God what to do." Their disagreement was not personal. It reflected a deep fracture in how humans understand the universe. One side believed science describes a world that exists independently. The other accepted that science describes only the relationship between the observer and what is observed. Hidden beneath this debate is an even more disturbing question. What is the role of consciousness? Is a conscious observer required for reality to collapse from possibility into actuality? Or is an inanimate measuring device sufficient? And if mere physical interaction is enough, where exactly is the boundary between observation and existence? To this day, there is no definitive answer. Quantum mechanics works flawlessly as a predictive tool, yet leaves its interpretation unresolved. The only certainty is this: particles do not follow ordinary logic. They refuse to be confined within the familiar frameworks of human intuition. They exist in a way that is mathematically precise, yet intuitively absurd. The quantum world, therefore, is not merely strange, it is rebellious. It breaks the assumption that reality must be clear, definite, and independent. It forces us to admit that the rules which help us understand everyday life may be crude approximations of a deeper, more complex, and more unsettling reality. And when foundational rules break, the question is no longer, how does the world work, but are we truly prepared to accept how it works? In everyday life, matter seems the most certain thing we know. A hard wall, a heavy stone, a body with clear shape. We touch matter, collide with it, are stopped by it. It is therefore natural that humans long believed matter to be the ultimate foundation of reality, the solid bricks from which everything is built. But as science digs deeper, layer by layer, that belief begins to waver. The ancient Greeks believed everything was composed of 4 elements: earth, water, fire, and air. Millennia later, we replaced this idea with atoms, tiny, indivisible particles. Then the 20th century arrived, and atoms themselves were no longer the end point. They fractured into electrons, protons, and neutrons. Those final bricks were crushed further into quarks, and nearly invisible particles like neutrinos, silently passing through matter without leaving a trace. Then came an even more shocking discovery. Even fundamental particles are not truly things. According to quantum mechanics and quantum field theory, what we call particles are merely localized excitations of invisible fields that permeate space and time. An electron is not a tiny dot existing on its own. It is a vibration, a ripple of energy in the electron field. A photon is not a bead of light, but a vibration of the electromagnetic field. At the deepest level, reality is not built from solid objects, but from oscillations. This completely changes how we understand matter. If all particles are just vibrations of fields, then matter is no longer something that exists in the traditional sense. It is a process, a dynamic phenomenon, a temporary configuration of energy. What we call a table, a mountain, or even our own bodies are simply stable patterns, repeating structures in a sea of quantum fields constantly in motion. Space itself is not empty. Even in a perfect vacuum, quantum fields persist. They fluctuate, giving rise to virtual particles that appear and vanish in times too short to observe directly. The vacuum, far from being nothing, is a restless foundation where reality is continuously emerging and dissolving. In this context, matter loses the solidity we once attributed to it. It is no longer the firm foundation of the world, but a fragile expression of deeper laws. A slight change in field structure, a different vibration, and matter may no longer exist as it once did. This also explains why familiar properties, hardness, mass, color, are not absolute. They arise from how particles and fields interact. Color does not exist within objects. It results from how electrons absorb and emit energy. Hardness is not proof of solidity, but the consequence of electromagnetic forces preventing atoms from passing through one another. The material world, it turns out, is merely the surface of a far deeper reality. What is unsettling is that these strange laws do not apply only to exotic particles in laboratories. They apply to everything, including you, every atom in your body, every electron moving through your brain cells obeys quantum rules. Your existence, at its most fundamental level, is a continuous quantum story, even if you are unaware of it. We do not perceive the world as a sea of vibrations because, at large scales, quantum effects are averaged out. Microscopic chaos is hidden by the enormous number of particles interacting at once. The macroscopic world appears stable not because quantum laws disappear, but because they are blurred. But the fact that we do not feel them does not mean they are not there. From this realization, a philosophical unease emerges. If matter is not solid, if it is only oscillating energy, then where is the boundary between existence and non-existence? A particle can emerge from the vacuum and vanish. A state can exist only as probability. Reality becomes not a collection of objects, but a continuous process of formation and dissolution. This forces us to reconsider the very foundation of the world. Perhaps what is truly fundamental is not matter, but relationships, interactions, information exchanged between fields. Perhaps things are simply the brain's way of simplifying a reality too complex for direct intuition. If so, the sense of certainty we feel about the material world may be an evolutionary illusion, a model good enough for survival, but not deep enough to reflect truth. We live in a smoothed, simplified reality, while beneath it lies a cold, alien world governed by rules we were never designed to intuitively understand. Matter is not stuff. It is a story the universe tells itself through quantum field vibrations. And when that story changes, reality changes with it. At this point, one thing becomes clear and unsettling. If matter is no longer a solid foundation, then what we approach next will be even more unstable. For when things dissolve into vibrations, the next unavoidable question is, what determines how those vibrations become the reality we experience? And that is where the story begins to approach even more dangerous concepts. When matter is no longer matter, when particles are fragile vibrations in invisible fields, an unavoidable question emerges. Can we ever know exactly what is happening in that world? The troubling answer is no, not because our instruments are insufficient, but because reality itself does not allow it. At the heart of this limit lies Heisenberg's uncertainty principle, one of the most unsettling pillars of quantum mechanics. According to it, you cannot simultaneously know a particle's exact position and momentum. The more precisely you measure one, the less information you have about the other. This is not a measurement flaw, nor a technological limitation. It is a fundamental feature of nature. In other words, the universe does not permit a complete picture. In classical physics, knowing enough initial information allows perfect prediction of the future. The world resembles a vast machine with predetermined motion. Quantum mechanics destroys this image. At its deepest level, reality is written not in certainties, but in probabilities, not what will happen, but what might happen and with what likelihood. The mathematical tool describing this world is the wave function. At first glance, it seems like a cold, abstract expression, but its meaning is deeply unsettling. The wave function does not describe where a particle is, it describes all the states it could be in. It is a map of possibilities, not of finalized reality. When no measurement is made, the wave function evolves smoothly, encompassing many possibilities at once. The particle has no definite position or trajectory. It exists as a superposition, both here and not here. But when a measurement occurs, something strange happens. The wave function collapses. From countless possibilities, only one outcome is recorded. The problem is that no equation in quantum mechanics smoothly describes this collapse. The equations tell us how the wave function evolves when unobserved, but falls silent at the most crucial moment, the moment reality chooses a definite form. Collapse appears to obey rules different from the theory's own laws. This creates a deep crack in the foundation of modern physics. Wave function collapse raises a dangerous question. What actually causes it? Is an inanimate measuring device enough? Does it require a system complex enough to record information? Or worse, does it require consciousness? If physical interaction alone suffices, then where is the boundary between observation and non-observation? Is every particle collision a measurement? If consciousness is required, what does that imply about humanity's role in the universe? Did reality exist before conscious beings arose? There is no accepted answer. Some interpretations claim the wave function never truly collapses. Instead, all possibilities continue to exist, and what we call a result is merely the observer's limited perspective. Other interpretations suggest collapse is real, but governed by unknown physical mechanisms yet to be discovered. Either way, the philosophical consequences remain. Reality, at its core, is not a complete picture waiting to be revealed. It is more like an unfinished symphony, where each measurement is a note played, and countless others will never be heard in the same version of the world. This makes the concept of knowing fragile. We are no longer neutral observers reading data from the universe. We are part of the process that creates that data. Every measurement not only gathers information, it eliminates innumerable other possibilities from the reality we experience. At a deeper level, uncertainty is not merely a technical feature. It is a statement about the nature of the universe. The universe does not commit to a single outcome until it is forced to. Ambiguity is its natural state, surrendered only when compelled to choose. Perhaps what truly unsettles scientists is not that we cannot know everything, but that reality itself may not know what it will become until the final moment. Uncertainty resides not in human ignorance, but in the structure of the world itself. When we accept this, the sense of a stable, predictable universe collapses, like the very wave function we are trying to understand. And when that foundation disappears, we face a deeper question. If reality is merely a set of possibilities waiting to be actualized, what determines which possibility becomes the world we live in? That question leads us to one of the most famous and haunting images in modern science, where the boundary between life and death, existence and non-existence, dissolves entirely. And that is where Schrödinger's cat awaits. There is an image that has haunted modern science for nearly a century. It did not come from a telescope or a particle accelerator. It came from the imagination of a physicist and became one of the most disturbing symbols of the quantum world. Schrödinger's cat. Imagine a sealed box, completely isolated from the outside world. Inside is a cat, a small amount of radioactive material, a Geiger counter, and a mechanism that kills the cat if the radioactive atom decays. According to quantum mechanics, before observation, the atom exists in superposition, both decayed and not decayed. Because the cat's fate depends on that atom, the cat too is dragged into superposition. It is both alive and dead, not metaphorically. Not because we lack information, but because, according to quantum logic, no definite state exists before observation. The cat is not mysterious in the sense of unknown. It is genuinely suspended between two mutually exclusive realities. Schrödinger did not propose this thought experiment to endorse the idea. He meant to expose the absurdity of applying quantum rules to the macroscopic world. Yet the paradox is this: as science advances, the cat becomes harder to dismiss. If particles obey superposition, if wave functions describe all physical systems, then somewhere there must be a boundary where the quantum world ends and the classical world begins. But for decades, no one has been able to identify that boundary. Why can an electron exist in multiple states but not a cat? At what size, at what level of complexity must reality choose a single outcome? And, more importantly, who or what forces it to choose? These questions strike at the heart of wave function collapse. In Schrödinger's scenario, the cat is entangled with a quantum system. Without observation, the entire system, atom, mechanism, cat, must be described by a single wave function containing both possibilities. No measurement, no distinction. Yet this clashes violently with our lived experience. We never see creatures that are half alive and half dead. We do not enter rooms where tables both exist and do not exist. Everyday reality appears immune to quantum ambiguity. So where does the ambiguity disappear? Some scientists argue the answer lies in decoherence, the process by which quantum systems lose superposition through interaction with their environment. The cat cannot maintain superposition because it constantly interacts with air, heat, light, and countless particles. Information about its state leaks into the environment, making the wave function appear collapsed. But decoherence only shifts the problem. It explains why we do not observe superposition at large scales, but not whether collapse truly occurs or merely appears due to our inability to track the entire system. In some interpretations, the cat never truly chooses life or death. Both possibilities continue to exist in different branches of reality. In one branch, the cat lives. In another, it dies. When the observer opens the box, they merely step into one branch, never perceiving the others. If this is true, Schrödinger's cat is not just a pitiful creature in a box. It is a symbol of a constantly branching universe, where each moment generates countless parallel realities. Other views are even more unsettling. Some serious hypotheses question whether consciousness plays a special role in collapse. Does an inanimate system suffice to finalize reality, or does a conscious subject matter? If consciousness is key, then what is the cat's state before the box is opened? Does it know whether it is alive or dead? Or is even its subjective experience suspended in uncertainty? These questions are not merely strange, they mark the boundary where physics collides with philosophy, and where science must admit its own uncertainty. Schrödinger's cat is no longer a thought experiment. It is a reminder that our most basic concepts, life, death, existence, may not be as simple as we believe. Perhaps the most disturbing possibility is not that the cat is both alive and dead, but that our own reality may once have been suspended in the same way, only choosing a definite form when observed, recorded, or experienced. If so, the world is not a finished story. It is a draft written moment by moment, where each act of observation locks reality into a single version while erasing countless others. Each time we look, measure, or become aware, we do not merely discover reality, we constrain it. Schrödinger's cat, therefore, does not reside in the box. It lives in the question the box raises, a question with no final answer, yet impossible to ignore. Because if the boundary between life and death can blur at the fundamental level, then the boundary between what is and what could be is far more fragile than we ever admitted. And when the lid of that box opens, what we confront is not merely the fate of a cat, but the nature of reality itself. If superposition and Schrödinger's cat render reality ambiguous, quantum entanglement is the moment when all notions of distance, separation, and independence collapse entirely. Imagine two particles created together in a quantum process. From that moment on, they become a single system, even if later separated by vast distances. They can be sent to opposite ends of the universe, millions of light years apart. Yet according to quantum mechanics, they remain linked in a way that cannot be broken. Measure the state of one particle, and the state of the other is instantly determined without delay, without signals traveling through space, without any classical mechanism. Einstein called this spooky action at a distance, and he hated it. According to everyday intuition, nothing can influence something else faster than the speed of light, a cornerstone of relativity. But entanglement seems to ignore that limit entirely. Information does not travel. It appears never to have been separated in the first place. This forces a terrifying question. Are two entangled particles truly separate entities? In the classical world, we divide everything. This object is here, that object is there. Space separates. But entanglement suggests that at the fundamental level, separation itself may be an illusion. Two particles, no matter how far apart, behave as a single system. Distance, in this case, loses meaning. Decades of experiments have confirmed this with increasing precision. Entanglement is not a theoretical curiosity. It has been demonstrated in laboratories. The results violate Bell inequalities, conditions any theory based on local realism must obey, and they are violated. This means you cannot simultaneously hold two beliefs. 1. Particles have definite states before measurement. 2. No influence travels faster than light. At least one must be false, possibly both. If particles lack definite states before measurement, then reality does not exist as we think. If non-local influences exist, then space is not a fundamental barrier. Either way, the familiar picture of the universe is severely distorted. Entanglement is therefore not just strange, it is a direct assault on the idea of independent reality. It suggests the world is not built from separate pieces, but from relationships, not things, but connections. In this view, a particle has no meaning in isolation. Its state can only be described relative to other particles. Reality is not a collection of objects, but a network of quantum correlations. This blurs the boundary between here and there. If entangled particles respond as one, then locality, the foundation of everyday experience, may be an emergent phenomenon, not an ultimate rule. Applied to larger scales, the implications grow even more unsettling. If particles can be entangled, then atoms, molecules, and even more complex systems may carry traces of such connections. In the early universe, everything was once part of a single quantum system, tightly interacting. As the universe expanded, those connections may have been stretched, not broken, but hidden. In other words, everything may once have been entangled with everything else. If true, then the sense of separation between humans and the world, between objects and space, between self and not self, may be a product of scale and perception. At the deepest level, reality may be a unified whole, indivisible in ways our intuition cannot grasp. Here physics begins to echo ancient philosophical questions. If the universe is non-local, if its parts are not truly independent, then linear causality, the idea that causes here produce effects there, must be rethought. This is not mysticism, it is the structure of reality as described by rigorous science. Entanglement does not allow faster-than-light communication, but it reveals that the universe is not built from isolated blocks. It is more like a seamless fabric than a mosaic. Tug one thread here, and the structure elsewhere is affected, not by force, but because it was never separate. Perhaps the most unsettling implication is this: if reality is non-local, then our experience of clear boundaries may be a limited interpretation. We perceive separate objects because our brains require simplicity to function. But beneath that surface, the universe may be an indivisible whole, where everything is related to everything else in ways that defy intuition. Entanglement, therefore, challenges not only science, but our sense of being in the world. It suggests that isolation, separation, even individuality may not be fundamental features of reality, only the way reality is allowed to appear to us. And when locality dissolves, the next question becomes unavoidable. If reality is a network of relationships, What truly exists, the objects themselves, or the relationships between them? That question leads us to an even deeper problem, where science begins to doubt the very notion of objective reality. After everything quantum mechanics has revealed, superposition, wave function collapse, non-local entanglement, science faces an uncomfortable truth. We have precise equations, but no single coherent story to explain them. Quantum mechanics works perfectly. It predicts experiments with astonishing accuracy. Yet when asked what it means, physicists fall into deep disagreement, not over numbers, but over the nature of reality itself. These disagreements are called interpretations of quantum mechanics. Each interpretation offers a radically different picture of the world, so different that they contradict one another and contradict human intuition in distinct ways. 1. The Copenhagen interpretation. Reality exists only when observed. This is the oldest interpretation associated with Niels Bohr and Werner Heisenberg, and the one most commonly taught, though rarely fully stated because it is too disturbing. According to Copenhagen, before observation, a quantum system has no definite state. It is not here or there, not a wave or a particle. It exists as a set of possibilities described by the wave function. Only when a measurement occurs does the wave function collapse and produce a concrete result. Reality, in this view, does not exist independently of observation. This does not necessarily mean human consciousness creates the world, but it implies that the measured system and the act of measurement cannot be separated. You cannot speak of reality without speaking of interaction. Copenhagen does not explain why collapse occurs. It simply says, this is how nature behaves. Accept it and calculate. Einstein hated this. God does not play dice, he insisted. To him, Copenhagen felt like philosophical surrender, a refusal to answer what reality truly is. Yet the disturbing fact remains. Copenhagen works. 2. The many worlds interpretation, no collapse, only branching. If Copenhagen claims reality is indeterminate until observed, the many worlds interpretation, proposed by Hugh Everett, takes the opposite path and may be even more shocking. According to this view, the wave function never collapses. Each time a measurement occurs, instead of selecting one outcome, the universe splits into multiple branches, each containing a different result. In one branch, the cat lives. In another, it dies. All outcomes are real. You do not perceive other branches, not because they do not exist, but because you split along with the universe. Each version of you experiences only one result. There is no randomness. Every possibility occurs. No branch is privileged as the real one. It is simply the one your consciousness inhabits. This interpretation resolves technical issues, especially collapse, but at a terrible cost, an almost infinite number of simultaneously existing realities. Every interaction, every quantum fluctuation, every microscopic event causes branching. Reality is not a single stream, but an endlessly diverging tree. This raises a chilling question. If all possibilities occur, what makes you you? Which version is truly real? 3. A fragmented reality, no single coherent story. Copenhagen says reality exists only when observed. Many worlds says all realities exist at once. These views cannot both be true in a philosophical sense. And the troubling part is this: no experiment currently can definitively distinguish between them. They make the same mathematical predictions. They differ only in how we interpret what the equations say about the world. This means that, at the deepest level, Science functions without knowing what it is actually describing. Reality, in this sense, has become fragmented, not because the world itself shattered, but because humans lack a unified conceptual framework to understand it. Some physicists choose Copenhagen for practicality. Others choose many worlds for mathematical consistency. Others explore hidden variables, pilot waves, or even the role of consciousness. There is no consensus, and perhaps that says more about the limits of human thought than about the universe itself. The most unsettling possibility is this: there may be no single correct picture of reality. Perhaps reality is not constructed to fit human intuition, language, or philosophy. Quantum mechanics does not say the world is strange. It says our way of thinking about the world is incomplete. And when interpretations compete without resolution, a suspicion arises: is reality something that exists independently, or merely a story we tell to connect scattered observations? If so, the next unavoidable question is, what is the role of the observer? Is consciousness merely a witness, or an inseparable part of the universe's structure? This is where science approaches its final boundary. After all equations, experiments, and conflicting interpretations, quantum mechanics leaves us with a question that cannot be avoided. One science has pushed aside for centuries because it is too dangerous. Who or what is observing? In classical physics, the observer has no special role. The world operates like a giant machine, and humans stand outside watching. Whether you look or not does not alter a planet's orbit or a falling stone. Quantum mechanics shatters that neutrality. At the quantum level, observation is no longer passive. It becomes part of the phenomenon itself. Not because humans magically create reality, but because the observed system cannot be separated from the act of observing it. This creates a disturbing gray zone. Without observation, does a definite reality exist at all? Some physicists attempt to soften the issue by claiming observation is merely physical interaction, a detector, a photon collision, a recording device. No consciousness required. But this explanation only pushes the problem back one step. Because then we must ask, when does an interaction become a definite outcome? Why does the microscopic world obey probabilities, while the macroscopic world appears certain? This is the measurement problem, one of the deepest mysteries of quantum mechanics. And it is here that consciousness quietly re-enters the discussion. Some thinkers suspected early on that consciousness cannot be fully removed from the equation. Eugene Wigner suggested that the observer's consciousness itself causes wave function collapse, not the device, not physical interaction, but the moment subjective experience arises. This idea makes many physicists uncomfortable. It smells of metaphysics. It threatens the boundary between science and philosophy, a boundary modern science fought hard to erect. But discomfort does not mean falsehood. To this day, no fully convincing explanation exists for why reality chooses a single outcome. Interpretations that avoid consciousness, Copenhagen, many worlds, hidden variables, all pay a price in increasingly strange assumptions. Consciousness thus becomes a ghost, banished from the laboratory, yet haunting foundational questions. The issue deepens when we realize that consciousness is the one thing we cannot doubt. You may doubt the external world, you may doubt measurements, but you cannot doubt that you are experiencing something. From this perspective, physical reality, the object science seeks to describe, may not be ultimate. It may emerge from a deeper layer where consciousness and information play central roles. Some modern approaches seriously consider this possibility, not spiritually, but informationally. In these models, reality is built not from matter, but from bits of information and relationships. Consciousness, rather than being a byproduct of matter, may be the way information experiences itself. This completely reverses intuition. Instead of consciousness emerges from the brain, the question becomes, is the brain an interface, a decoder for a deeper reality? If so, the observer is no longer an outsider. We do not look at the universe from without. The universe looks at itself through us. Here science begins to echo classical philosophy, from Descartes' "I think, therefore I am," to Kant's idea that space and time may be structures of perception rather than of the world in itself. Quantum mechanics does not claim consciousness creates reality, but it does not allow us to easily remove consciousness either. It places the observer in an uncomfortable position, neither central to the universe nor peripheral. This suggests a troubling possibility. Reality may be incomplete without experience. A universe unobserved, at the deepest level, may not be a full universe. If so, existence is not merely about matter, but about the relationship between matter and awareness. Science, accustomed to third-person descriptions, now faces an uncomfortable truth. It cannot fully understand the universe while ignoring the first-person perspective. Consciousness is no longer a side question. It becomes the final boundary. And as science approaches that boundary, one last question forms, not only for physicists, but for anyone who exists. If reality requires an observer to become definite, what happens when there is no one left to observe? That question is not only about the universe, it is about our place within it. And that is where this journey moves toward its conclusion. Eventually, we reach a point where science can no longer proceed in its familiar way. Not because it is wrong, not because it has failed, but because the questions ahead are no longer questions for equations. Quantum mechanics has done what no previous science achieved. It has not only changed our understanding of the world, but shaken the very idea of what understanding means. It gives us astonishingly precise numbers, yet strips away the certainty that those numbers describe a familiar reality. We know how to calculate probabilities, but we do not know what truly happens. We know measurement outcomes, but we do not know what exists before measurement. At this point, science falls silent not for lack of data, but because its language is no longer sufficient. When conflicting interpretations coexist, when the observer cannot be removed, when reality is simultaneously wave and particle, possibility and relation, the question, what is the world, no longer has a single answer. And this is the moment humanity must turn inward. For thousands of years, we sought certainty. We wanted a stable universe existing independently, governed by objective laws without our presence. A world where humans were humble spectators. Quantum mechanics does not grant us that humility. It grants us responsibility, not because we control the universe, but because we cannot stand outside it. If reality becomes definite only through interaction, if the world cannot be separated from experience, then human existence is no longer a footnote. We are not the center, but we are not outsiders. We are part of the story the universe tells about itself. This is not mysticism, it is something deeper, the meaning of presence. When science no longer answers, what remains is not blind belief, but honesty. Honesty that some questions cannot be forced into equations. Honesty that subjective experience, once dismissed as unscientific, may be a missing piece, not to replace science, but to complete it. Perhaps reality is not something out there waiting to be fully discovered. Perhaps it is a process, one where observation, interaction, and meaning together form what we call the world. If so, the final question is not, what is the universe? But how are we participating in it? Science gives us tools, philosophy gives us frameworks. But experience, living itself, is where everything converges. Faced with an uncertain, not fully objective, not easily separable universe, humanity has two choices: fear or acceptance. Acceptance that ambiguity is not the enemy of knowledge, but its condition. That not knowing everything does not mean meaninglessness. That lacking final answers does not mean emptiness. Perhaps what remains when science stops is wonder, not naive wonder, but mature wonder, the kind that allows us to live in a universe not fully explained, without despair. A universe where reality is not a rigid wall, but a surface of water, reflective, shifting, responsive to perspective. And in that surface, we do not see only particles, waves, or equations. We see ourselves, part of the whole, not special yet irreplaceable. Science may not give us the final answer, but it gives us something else, perhaps more important: humility before the unknown. And in that space, where answers end, humanity begins to ask, not as scientists, but as beings who exist, if reality is not entirely certain, how shall we live within it? That question does not need an equation. It needs to be lived, and perhaps that is all that remains. If you are drawn to questions science has not yet dared to answer, if you wish to see the universe not only through knowledge, but through contemplation, subscribe and follow the channel, so we may continue exploring the boundaries of reality together.